Okay, welcome back. So it's possible that a lot of people are going to think that this chapter is out of order. I don't know. I haven't really decided what order I like best for the chapter because in this chapter we're going to, or in this section, we're going to assume that we've been provided with a fundamental set of solutions to an associated homogeneous ODE, and then we want to find a particular solution. So by that, what I mean to say is, suppose we already have an FSS. We're going to find out how to find these later, but for now, let's just assume that we actually have one. And given that we have one, how could we find? Can we find YP, right? So an FSS is going to give us YH. We already know that from the previous section. So the FSS and YH in many ways are one and the same thing. So fundamental set and the general homogeneous solution are kind of the same thing. Can we find YP? So given a fundamental set, how easy is it to find a particular solution? And it turns out it's actually pretty easy. It's not foolproof. We actually have to compute a lot of things and compute antiderivatives, but minus those tiny little obstacles, because they're not that large. We have beautiful formulas which will let us solve it for us. So let's start here, and we're going to define this thing called the Wronskian. So probably everybody else in some other ODEs courses hates this word because it's thrown all over the place and it's kind of tricky to use sometimes, but I actually like it. I mean, maybe not the word Wronskian, it's fun to say, but I like the idea of the Wronskian matrix. I think it's a very elegant way to phrase how to solve a lot of these ODEs in one dimension. So the Wronskian matrix is constructed from a fundamental set of solutions. So given some fundamental set of solutions, I'm going to produce a matrix, and it's going to be a square matrix. I'm going to produce that matrix by lining up my fundamental set. Let's look at this. So I just line up the fundamental set across the top of my matrix, and then I start to take derivatives. So one derivative, two derivatives, dot, dot, dot. We're going to end up with n minus 1 derivatives. Why n minus 1? Well, because we started out with 0 derivatives. So the total length of derivatives, or the total number of rows I have in my matrix, is n, because if I start my indexing at 0 and go up to n minus 1, that's still n pieces. So I'm just going to produce this matrix out of my fundamental set and then all of the derivatives. And in fact, you would think that the order of the fundamental set matters here, but it doesn't. So order doesn't actually matter, so long as you preserve it when you're taking derivatives below. Doesn't matter. So long as you preserve your order, in column wise, you can permute the columns themselves, and you'll still get a perfectly valid Wronskian matrix. So this thing isn't unique, but it's unique up to order. Yeah. All right. So then the Wronskian determinant is the determinant of this matrix. So both of the matrix YW, I call it YW here. Everybody will have a different notation for the Wronskian matrix. I just use a capital letter for whatever my function variable that I'm looking for is. And then the determinant, I usually just use the capital W for Wronskian, because sometimes people will just refer to the determinant itself as the Wronskian, and I don't even know what they call the matrix then. But the Wronskian determinant is the determinant of this matrix. Okay, and then I have this remark here that's a little bit important to recall. So the Wronskian matrix and the Wronskian determinant, so YW and W, are notated by only letters. We should recall that they're both actually functions of the independent variable. If it's x or t or whatever the independent variable of these functions are, both the Wronskian matrix and the determinant actually evolve. Okay, so this is like a function of t, that's a function of t. Because my inputs to those were also functions of t or functions of x or whatever. And so we can actually play around with these things as functions, not just as objects. Okay, so let's just keep that in mind, even though we drop the dependence. This proposition is fantastic. This is kind of why I've ordered the course the way I have. It's that the Wronskian matrix is a fundamental matrix. So if we jump back a chapter to chapter 6, we really cared about these fundamental matrices for the systems. And it turns out that this Wronskian matrix that we've just produced is a fundamental matrix for the system that would be produced had we used theorem 4.4.1 on our original nth order ODE in one dimension. And so that's kind of the big tie-in between last chapter and this chapter, is that they're two sides of the same coin. I suppose this entire chapter is a bunch of specific examples of last chapter, which is why last chapter was the sledgehammer. But you can think about this Wronskian matrix as the fundamental matrix. And that's actually one of your exercises, is to prove that. So let's look at the example here. This is the same ODE that we were working with in the last section. So you should feel very familiar with its solutions, or its fundamental set of solutions, the cosine and sine with some t's and logs sitting around. And if I scroll down a little bit, we can construct the Wronskian matrix from this by computing the following. So we go with we order the fundamental set y1, y2 in the first column, and then we take its derivative for the first row, and then we take a derivative for the second row. And we just do this by computing, and we get something that's big, but it's definitely something that's computable, especially if you're using the Wolfram Cloud to help you out. So it's not the end of the world to compute something like this. And then once we have it, we can take the Wronskian determinant, and it's kind of fascinating to see how much the determinant simplifies from the matrix. And this is kind of an interesting thing to talk about for some strange reason. Obviously the reason's not that strange, we could talk about it in class, but the Wronskian determinant's always way more elegant than the fundamental set. The Wronskian determinant, all sorts of beautiful like identities and properties always show up and cancel a bunch of things, and so you get something like root 3 over 2 t to the minus 2 instead of all of this nonsense that you get in the Wronskian matrix. All right, so here's the next theorem is the theorem for the section. So I mean, if you don't want to miss anything from this section, it's this theorem. Pay attention to this theorem alone. We need the previous definition to use the theorem, but that's about it. And unfortunately, it splits the page here because I have this nice piece that's the jth column, and I'll write it on the next page for you. But basically what we're going to do is we're going to find a particular solution. Maybe I'll write that out. What does it say? We can find a particular solution using the Wronskian matrix. And that is absolutely fascinating, and the determinant. So this Wronskian matrix really lets us extract a particular solution. And the nice thing is that the Wronskian matrix, all we needed was the fundamental set to produce it. So all of a sudden, given a fundamental set, I can extract a particular solution. And I'll show you how we do that. So the first thing we do is define another collection of matrices, which I call the J-modified Wronskian matrices. That definition is not terribly common, but here's the jth column. I'll put that back. Jth column. So what we do, I'm going to call these y sub w sub j. So the Wronskian matrix yw, but it's the jth modified one. The jth column gets replaced with zeros and then a ratio ft over mnt. So let's describe what this ft over mnt actually is. Let me scroll back up. Let's look at this. This is our inhomogeneous ODE. And I want it, that's what I'll say, I want the leading, i.e. the highest order term to have a coefficient of 1. Okay, so if the highest order term does not have a coefficient of 1, hence divide by what is the scalar multiple on the highest order term? That's the n term here. So you divide by m sub n of t. And so the right hand side is f of t divided by m sub n of t. And so really all the reason why the bottom component of the modified Wronskian matrix is f divided by m sub n, it's because I need the leading order term to be a 1. And then everything else works really well. So I have to divide by the top scalar multiplying function, and then I replace the jth column, y sub w sub j. The jth column gets replaced. Okay, so we also have associated Wronskian determinants to these w sub j's. I'm just going to take a determinant here and call that w sub j rather than y sub w sub j. And the theorem statement, this is the best part about the theorem, is it says the particular solution, any particular solution, right? A particular solution can be completely calculated as it's kind of a linear combination of the fundamental set. These y sub j's are still the y sub j's from the fundamental set of solutions, but now what do I have going on as coefficients is that these coefficients depend on time. They're not constants the way that I normally would have if I were finding the homogeneous solution. So now the constants depend on time, and this is where we get the term variation of parameters, because, so I'll put that in quotes, because the parameters in the span of the fundamental set of solutions vary in time. So the fact that the span no longer is fixed in time, but the span varies in time, or at least the coefficients in the span are allowed to vary in time, that's why we call it variation of parameters. But we can calculate it just from the determinant of these modified Wronskian matrices, right? So each one has that special J inside of it, and that's exactly associated to that term of the fundamental set of solutions, right? That's really the missing term here. Term is y sub j. So the missing term is the y that comes out and multiplies what I end up calculating here as the antiderivative. It's an antiderivative of the j modified Wronskian determinant divided by the regular Wronskian itself. So I take that little ratio, compute its antiderivative, and that's what my coefficient on the yj term is. And that will produce a particular solution for me. And I know you are all getting really excited to prove this because it doesn't seem complicated at all. Yeah, so you have a very long exercise to complete to prove this. I walk you through it relatively well, but it's still a little bit complicated. But it's really fun to see just where this whole idea comes from, because it's not so clear upon initial inspection why this should necessarily produce a particular solution. Okay, so something that's interesting is that now I can compute this. I shouldn't say something that's interesting. All right, so now I can compute this. Let's look at an example. We're jumping back to this favorite example we've had so far, but now, right, so now recall I had claimed this function, I think it was 1/7 t squared plus 2/3 t minus 1 or plus 1 or something like that was a fundamental or was a particular solution to this. We're going to see where that comes from now. So we're going to see how we can actually find a particular solution to this inhomogeneous ODE. So how do I find a particular solution where the right-hand side is t squared plus 2t plus 1? Well, you use the fundamental set with the theorem above. So what we're going to do is we need to, and this should be m sub 2, we need to divide the left-hand side by both sides by the leading order coefficient. So if I divide everything by t squared, that actually takes me to the ODE y double prime plus 2 over t y prime plus 1 over t squared y equals 1 plus 2 over t plus 1 over t squared. And that's what's going to go into my modified Wronskian matrices. Okay, so if I jump down here, my modified Wronskian matrices, I'm using negative exponents to make my life a little easier, but I'm plugging f divided by the leading order term, so the right-hand side divided by the leading order coefficient. I plug that in to the first column to get my first modified Wronskian matrix, and then I plug it in to the second column to get my second modified Wronskian matrix, right? And then where are these other terms coming from? That's just y2 and y2 prime from my fundamental set. This is y1 and y1 prime from my fundamental set. So I'm constructing the two modified matrices, and then I'm going to calculate their determinants. And unfortunately, when it's not the true Wronskian, our determinants aren't nearly as pretty. But I calculate both of their determinants, and then I also have, right, we recall our Wronskian from before had this nice determinant of root 3 over 2 t to the minus 2, and I take ratios and integrate those. So if I go ahead, I know this is a lot of integration to do. That's why Wolfram Cloud is our best friend. So if I go ahead and I take the ratios, right, this is the ratio of W1 to W, and I actually take the antiderivative, same here, I have the ratio of W2 to W, I take their antiderivatives and I get some pretty nasty terms, but they're there, and it turns out those are the coefficients for y1 and y2 respectively that will give me a particular solution. And so if I scroll down and I put those in as coefficients on y1, so this is here the coefficient that I just calculated, and there's y1. I then have a new coefficient for the second round of Wronskian business, and then y2. And I simplify those. They look just terrible, don't they? But if I simplify them, it turns out they really simplify. You get 1/7 t squared, 2/3 t, and 1. And you should start to see how these actually simplified, because some terms cancel. I have a cosine sine term there, and I have a cosine sine term there, and notice there's a minus sign and a plus sign. It turns out those terms completely cancel. And then I have a cosine squared term here and a sine squared term here. And what do we know about sine squared and cosine squared? They add up to 1. And so all we pick up actually is these coefficients perfectly, multiplied by 1, which is where our 1/7 t squared 2/3 t and 1 comes from. So yeah, this is actually a really like strange procedure because we get some really ugly answers right away, but when we simplify everything, we actually get a particular solution, and it has a relatively elegant form, so long as we can manage to simplify it correctly. Okay, so with that said, I have a new proposition, which I'm saying will calculate the general solution of the nth order linear ODE in one dimension. So I don't care if I'm homogeneous or inhomogeneous, but this really provides a procedure on how I should always think about solving ODEs in one dimension. I'm going to convert, step one is I'm going to convert to the associated homogeneous ODE, and then I'm going to find n linearly independent solutions to form a fundamental set. So that's always my first step. First step in solving ODEs is to find an FSS for the associated homogeneous ODE. That's always the first step. And then my second step is actually really easy so long as I know how to compute antiderivatives. Because if I compute all of my modified Wronskian determinants and then antiderivatives and I just put them in front of my fundamental set, all of a sudden I've gained a particular solution, which really means that my true general solution just takes this form. All I have to do is consider this form, and then there's my solution. So if I find an FSS, this form will give me the solution. So basically, step one was find an FSS, step two is right here. So long as we know how to compute the Wronskian determinants and the antiderivative. And that's why I have this remark here, saying that a proper understanding and utilization of the above proposition is the primary purpose of a standard course in ODEs. So if you leave this course and somebody's like, oh, you took a course in ODEs, they're basically going to expect that you knew the previous proposition, and that's it. So if you have the proper understanding and utilization of that previous proposition, you'll have succeeded in the eyes of most people who expect you to have completed an ODEs course. So basically then, step one was find an FSS. We haven't even talked about finding an FSS. That's what the rest of this chapter is all about, is 7.3, 4, and 5. In particular, 4 and 5, how can I find an FSS for some very special ODEs? So in particular, we're going to look at the ones with constant coefficients, and then there's a fancy name called Cauchy-Euler type that we can also find an FSS for. Turns out 7.3, turns out all first order linear in one dimension. So first order, one dimension, the easiest thing to solve. So that's where we're going to get next, but then we'll eventually talk about FSSs. Okay, that's all I have. Thanks for sticking with me. I'll see you in class.